Good afternoon, everybody. My name is Mikael Vidstedt. I manage the Java virtual machine team at Oracle, and I'm here to talk to you a bit about Java in a world of containers. The first slide here is the obligatory Oracle disclaimer slide. It basically says that everything I'm about to tell you is a lie, so don't base any business decisions on it. The real agenda we're going to go through covers this. I'll talk a bit about Java in a world of containers on a high level, what we're expecting and what we're seeing, the trends in the industry. Something about how Docker containers are created, setting sort of the context and explaining some of the basic concepts because the rest of the presentation will cover a lot of Docker containers and how to work with them. I'll say something about creating custom JREs, Java runtime environments, and something about optimizing Docker image size and how you can use the tooling that we have in the JDK to do that. And then finally mention a few of the things that we have worked on in Java that are specifically targeting Docker and container environments. So starting with Java in a world of containers on a high level, in a world of containers, in cloud environments, we are expecting a few different things. So the first one we're expecting is that safety and security is going to become increasingly more important. Making sure that your data is safe and that everything works like it should is extremely important. And we're also expecting a few different types of sprawl in this environment. And what I mean by that is that we're going to see many different instances, not always the same applications running, but multiple different applications. Heterogeneous machines. Not all the machines will look the same. They may have different memory configurations, different CPUs. They may even have different CPU architectures, very different types of hardware. And also very different configurations for the containers as well. So a lot of differences in this world, a lot of different configurations and things happening. We strongly believe that Java is uniquely positioned to work well in this type of environment. It is, after all, a managed language and runtime, which means that you get a lot of the safety and security by design built into the Java runtime. The JVM makes your Java application hardware and operating system agnostic. So you can run it across all of these different configurations and it will just work. You don't have to rewrite your application specifically for new hardware. It's reliable. We spend a lot of time testing and making sure that the binaries we provide to you work well and are compliant and have all these features in them so that just works so that you don't have to care about that. And it's also very adaptive. So the JVM will automatically discover when it starts up what type of environment it's running in and how it should configure itself. On top of that, we have a very, very rich ecosystem built up in Java. There are many different libraries, many different vendors that provide functionality and libraries and frameworks for you to use. So we are committed to keeping Java vibrant and make sure that it remains the #1 choice for deploying applications in container environments. So I'm going to say something quickly about creating Docker images and using Docker. So first I'm going to ask a question. How many people in here have heard about, on some level, Docker before? Okay, a few hands. How many people have created a Docker image? Okay, so a few of you have. That's good. I will just go through this on a high level. This is not meant to be covering in detail how this works, but I will say something on a high level just to set the context again for the rest of the presentation. So in order to create a Docker image, normally what you start with is something like this. So in a directory somewhere, you place a few different files. The first one is a Docker file. I'll cover on the next slide what goes into that file. It's effectively a text file with some instructions in it. You place the files that you want to add to your Docker image. And for those of you who do not know Docker, it's a few different things. The concept of Docker is everything from a company to a technology to a hub or a repository, Docker hub, where you can store Docker images. So it's a few different things. In this example here, what I'm going to do is to create a Docker image, which is something that you can do ahead of time, long before you are actually running your application. And I'm going to put Java in there, and I'm going to put a very simple Java application in there. In this case, it's Hello World, so it doesn't get more simple than that. Inside of the Docker file, you add some instructions about what should happen when you build your Docker image. The first one is which base image to build this from. In my case, since I'm from Oracle, I'm using Oracle Linux, but you could use any Linux distribution here, and it will work equally well. I'm also saying in these instructions that once you have the base image, but on top of that, I want you to put the JDK, so the Java installation. And on top of that, I want to put the Java application as well. In this case, again, Hello World. And I'm also setting it up so that when the Docker container is later instantiated and started up, it will automatically run Hello World for me. The way this works with using the Docker command line is that you have two different phases, two different steps. The first one is the build step, which again you can execute ahead of time, maybe hours, maybe days, or even months before you want to run your actual application. And this is just packaging everything up so that you later can create containers based on this template image. The second step is the actual run of the image itself, the instantiation. Here is where you actually create a live image with the JVM process inside of it. And as you can see here, when I do that, it starts up Java and then it prints out Hello World, much like you'd expect. So these are sort of fundamental concepts to Docker. I hope it adds some amount of context to the upcoming slides. You don't need to understand it all in detail. Now I want to talk a bit about creating custom Java runtime environments. So in JDK 9, we added some functionality to help improve on this. And to start with, if you start out with, and just do the simple thing without really using this functionality, and you want to create a Java Docker image, and you just put the whole JDK in there, you end up with an image that is at least 600 megabytes in size. So inside of that image, you have all the Java functionality we've worked so hard over the years to add. So it has all the bells and whistles, all the great functionality that makes up Java, all the things you do want. So Java Lang, Java Util, all the packages that you're used to depending on. But it also has a lot of functionality that maybe you don't need. Corba, for example, is something that we find very few people using. So what we'd like to do is to enable you to build your own JREs and only include the functionality that you actually need. And this makes for a smaller image and also a more secure image because you're not including functionality that you actually don't need. So in JDK 9, which was released last September, we introduced a module system. This is Project Jigsaw. And what the module system allows you to do is to specify which modules you want to include. And in my example here, I have an application. The green box is an example application. And it has a dependency on two different modules. In this case, it's Java SQL Rosette and Java Activation. Those modules in turn have dependencies on other modules. And the functionality we have automatically figures out and calculates which modules need to be included. So even if you just depend on the top two modules, it will figure out the rest and actually include all the modules that in turn have dependencies. And what you end up with, if we remove the modules that are now not needed anymore, is, as you can see, a much smaller set of modules, which still will run your Java application just fine. So as I mentioned, this is something we introduced in JDK 9. It allows you to, again, create these custom JREs, custom Java runtime environment images. And I should say also that there's one module that is special. It's the one at the very bottom here called java.base. That module contains things like Java lang object. It's fundamental and mandatory functionality. So no matter which JRE you create, that module must be included. And I'll refer to that a bit later in the slides as well. So if we look at what this looks like on the command line, here's an example. So the tool I referred to that calculates this dependency graph and extracts the modules you need is called jLink. And there are a few options that you can specify. I have an example here where I'm including only, as I mentioned, the java.base modules. That's the one mandatory module that always needs to be included. And I'm asking jLink to produce binaries and put them in a directory called my.jre. And after that, once I've done that, I can run Java applications, like Hello World, for example, using that custom JRE. I should mention that the Java application here does not need to be module aware. So you can take existing applications that you have today that have not yet been upgraded to or been made aware of the modules that we introduced in 9 and still run them in this exact way. Now, one of the obvious questions is, how do I know which modules to include? Which modules does my application depend on? So it turns out that we have a tool for that as well. And that tool is called JDeps. You can specify to JDeps a class file or a jar file. In this case, I'm giving it a Tomcat API jar that I found. And the tool will produce a list of the modules that the application depends on. So using this, you can easily understand and see which modules your application actually depends on. And then you can use the jLink command to create a custom JRE that only includes those specific modules. So that's sort of the background to how you can create your own custom JREs. And over the next few slides, I'll go through a bit about how you can optimize the size of these images using this functionality. So to start with, let's look at what a simple Docker image would look like if you don't optimize it. So typically what you do is you'd start with a Linux distribution, like Oracle Linux in this case, and you'd add the full JDK. So this is what you'd typically do before JDK 9 and before the module system was introduced. And as you can see, the resulting image on disk is approximately 800 megabytes in size. So that's a bit on the big side, if you ask me. So let's see what we can do to optimize that and reduce the size of the image. So the first thing to look at is obviously the JDK itself. So we have this new functionality that we introduced, and let's see what we can, what kind of savings we can get using that tooling. So here I have 3 different types of Java runtimes. The bar on the left shows the full JDK. It's the exact same blue bar you saw on the earlier slide, or maybe it was green. And I also have one JRE that only includes this mandatory java.base module. And I have one that we call netty. This is effectively a version or a set of modules that is expected to cover the vast majority of the Java applications you have. So if you have a typical web service, for example, running on netty, you would find that this set of modules is probably the set of modules you're looking for. So a relatively small set of modules compared to the full JDK. And as you can see, by using this functionality, we are reducing the size significantly. So the java.base case is more than 10 times smaller. And netty, even though it includes this additional small set of modules, is still very, very small comparatively. This size can be improved further. I'm not going to go into the details, but there are ways of trimming this down even further. But if we look at what we ended up with now, we see that the base image is now suddenly the big part of the image. So if we want to reduce this size further, that's probably where we should go next. And I will say, just for completeness, that optimizing the size is not necessarily something you absolutely have to do. It very much depends on your exact use case. If, for example, you have an application that is very static in nature, it basically never changes, you don't upgrade it, you build it once, and then you run it for several months or maybe years, then maybe updating or performing these optimizations is not so important. However, if you have an application that frequently changes, maybe it is on the fly created because some data comes in, and you need to distribute this image to many, many different machines on your network, then size is suddenly can be a bottleneck, and it may be very important to reduce the size so that you don't have to copy so much data across the network. So coming back to the base image here, the first bar on the left here is a full Oracle Linux installation or distribution. It's the base image that contains all the functionality from Oracle Linux. But in order to run Java, as long as your Java application runs, you don't need all that additional functionality. So much like the module system in Java, we can look at reducing the size of the Linux distribution by simply not including all the stuff that we're not interested in. And in this case at Oracle, we have something called a slim version of Linux. And in this case, it's the Oracle 7 slim version. And it basically just contains the bare minimum to get you going. And as you can see, that reduces the size significantly. So now we're down to 150, 60 megabytes or something like that. So what if we want to do better than that? Well, it turns out that there is a Linux distribution called Alpine Linux. Alpine Linux, from their webpage, if you go there, they're saying that they're small, simple, and secure. And one of the things that makes this Linux distribution special for us is that it is using something called the Muscle C library. Normally, in a Linux distribution, you'd find the GNU C library. That's basically what all Linux distributions typically use. So this one is special in that it uses Muscle. And what that means for us on the Java side is that we do need to provide some special binaries. We need to translate and adapt the Java code we have to work together with the Muscle C library. And to do that, we're doing that in the context of an OpenJDK project called Portola. As you can see here, by using the Alpine Linux distribution and the base image for that, we're now going down from 118 megs for the slim version of Oracle Linux down to a very, very small base image. As a matter of fact, it's only 4 megabytes in size. And this still runs Java just fine. You do not have all the services around it. You don't have a printer daemon, for example, or strange things like that. But it still runs your Java application just fine because the JVM abstracts everything and makes sure that Java runs well in this environment as well. The project, the functionality of porting the JDK to Muscle is taking place in the Portola project, and you can go read up on the status of this project. I happen to be the project lead for this project. So I care deeply about this. And I'd like to ask you a couple of questions. So the first one is there any interest in this room for a port to Alpine and for this kind of size reduction? Okay, not that many hands, but a few. The other thing I normally ask is if anybody's interested in helping maintain this port, because obviously there is still work in making sure that it continues to work over time as we change things around. But that's good to know. Thank you. So we have now reduced the size down significantly. But the question is, and I should say that there are tricks we can play to reduce this even further, but it is starting to get very complicated. So the question is, can we do better? And in that case, how? And it turns out that this is not the best we can do. We can actually improve this. And we can do that using another trick. So we have looked at a single instance and how to bring down the size of a single instance. But in a cloud environment, using containers, what we expect is that people will run the same Java applications and have many, many, many instances of the same application running at the same time. Or at least very, very similar applications that share a lot of the same libraries. And if you look at what's happening on the operating system level, there's already a concept called shared libraries. So by using these shared libraries, the operating system is in the background sharing data across multiple different processes. And for the native libraries in the JDK, we already get that sharing because the operating system does that for us. But wouldn't it be nice if we could in some way share Java class data as well? And we do have functionality that does exactly that. It is called class data sharing, and it works in a very similar way to how operating system libraries work. So when the JVM starts up and it starts executing the application, it is loading classes. And in order to make sure that the runtime is performant, that we have good performance once the application is up and running, what the JVM does is to take the data from the class files and store it in memory in a format that is more efficient. And what class data sharing does is to take that data, the data that is now in a more efficient form, and store that back down to disk. And there are two benefits we get out of this. The first one is sharing across processes. So again, very much like operating system shared libraries. The second benefit we get is startup time. Because instead of now having to do this translation every time the instance starts up, it's done once ahead of time. And then this archive is loaded into memory and the data is already on the same format. And it turns out that class loading and this type of translation that we do is one of the most costly parts of startup. So using this, we can now share data across instances and also improve on startup. And the nice part about all of this is that it also works across container boundaries. It's not just for processes, it's also for processes in different containers. So looking at some performance numbers for the CDS, the class data sharing functionality, this is running a WebLogic server web service application. And on the left, you have the startup time improvements. Now, clearly, this depends on your exact application. But typically, what we're seeing is something in the order of 20 to 30% faster startup. In some cases, even as much as 50%. So it's very, very noticeable, a very, very good improvement. On the right-hand side, you're seeing the footprint savings. And it may not look like a lot, but if you take into account the fact that you may be running hundreds or thousands of these instances, and you start saving 10%, let's say, of memory footprint, that does add up. So if you have a data center with hundreds of thousands of servers, and you can save 10% of memory, that will translate into real dollars, real money. Because memory turns out to be one of the most costly things to buy and to power and to cool down in the data center. So class data sharing addresses the class data part of the data in memory. But what we'd also like to share is code. And very specifically, the JIT, or just-in-time optimized code that we produce when an application is running. And we have introduced experimental functionality to do exactly that. We call it ahead-of-time compilation. And basically what it does is to take your Java application and compile it to this highly optimized code and then store that code in an archive, much like the class data sharing functionality does. As I mentioned, this is still experimental. We're working on productizing it, but we are seeing good improvements here as well, both in sharing and in startup time improvements. For the last section, I will talk a bit about improvements we've made to Java that are specifically targeting Docker and Docker-like container environments. I have a link here on the slide which takes you to a blog that one of my esteemed colleagues has put together. His name is Matthew Gilliard, and I highly encourage you to go look at that. It's a very nice summary of the improvements we've made and some of the numbers that you're seeing. So I'll cover some of it in the next slides, but I will say that the blog entry is something that you absolutely should have a look at. The first part that we have looked at is making sure that the JVM and that Java respects and honors the resource limits that you set up using Docker. So when you start up a Docker container, you can say things like, I only want this instance to be able to use 2 CPUs, or maybe 128 megabytes of memory. And it turns out that this is not something that just works. It is something that we had to add explicit support for in Java to make sure that the JVM actually honors these values. Yes. I will say that I say Docker a lot, and I also mentioned that Docker-like container environments. From the JVM perspective, it is actually not important that it is Docker we're talking about. The JVM only sees C groups and namespaces, which are Linux concepts that Docker uses to control the containers. But other container technologies, similar container technologies, also use those concepts in Linux. So what we have done is to get the functionality to work well for C groups and namespaces, and then the rest sort of comes naturally. I mentioned that you can specify the CPU resources when you start up Docker. And the way you do that, there are a few different options. The first one is to use an option, and these are Docker command line options, not Java command line options. The first one is using CPU set CPUs. So that's setting the number of CPUs that the Docker container is allowed to use. But there are other ways of specifying it as well. So there are both shares, and there's a CPU quota that has similar functionality. Starting with JDK 10, we are now honoring those settings. So when you start up Java, the JVM will notice that it's running in a container environment, look at the right numbers and see how many CPUs it's allowed to use. In the past, it would look at how many CPUs the machine as a whole has, not the ones that the container is allowed to use. So this is a very good improvement, and obviously means that Java works well out of the box in container environments like this. These numbers are also reflected in a few different places in Java itself. So for example, in Java Lang runtime, there's an available processors method. And with this functionality, that number will now also reflect the settings that you gave Docker when you created the container. We also have a fork join pool internally in the Java libraries. And that pool is also sized now according to the number of CPUs that you have specified. And finally, inside of the JVM, we also have a number of internal concepts and especially thread pools. These are threads that are used for things like garbage collection or compilation. And those are also now sized according to the CPU settings for Docker. A lot of libraries and frameworks already use these other primitives, runtime available processors or the fork join pool. So since we have now enabled and make sure that those primitives behave the right way, these other frameworks and libraries will automatically behave like you'd expect and honor those exact same settings. The other aspect we have improved on is memory settings. So much like CPUs, you can also specify the amount of memory that the Docker container is allowed to use. And much like CPUs, if we don't add any explicit support in Java, we'd just look at how much memory is available on the whole machine and size the Java heap and internal structures according to that number. But if you want to run multiple containers on the same machine, that obviously means that we're now using too much memory. We're setting up the heap to be too large. So with this new functionality, we're now honoring the settings for memory as well. And I'll also just mention that we had a few different arguments that you could use to specify how much memory should be used internally in the VM. There was a version of those arguments that was very hard to use. And recently we added another version of those arguments that are much easier to use. So instead of talking about ratios, which were hard to balance and get right, you can now specify the percentage instead. So you can read up more on that in the issue I'm linking to here. The final thing I want to mention is that we're also looking at making sure that our serviceability and manageability tools work well in container environments as well. So we have all the discovery mechanisms. We have an attach framework. We have a tool called JCMD and JPS. These are tools that live normally in the bin directory in the JDK. And much like with CPUs and memory, we had to make some changes to these tools to make sure that they work across container boundaries as well. There's more to come here. So with the recent changes we've made, Java is now working well in container environments. But as I mentioned on an earlier slide, we are committed to making sure that Java remains the first choice here. So there's much more to come in this space. Keep an eye on what's coming. So, quick summary. I talked about what happens if you start just with the simple approach to creating Docker images. You'll typically end up with very large images that contain a lot of functionality that you don't necessarily need or want. There are tools now for creating your custom JREs and creating smaller versions of these images that only contain the functionality that you actually depend on. And in this specific case of a simple Java application that only uses java.base, we can actually get it down to approximately 38 megabytes in size. There are tricks we can play to reduce that even further, but 38 megabytes is starting to get small enough, I will say. The Java application will obviously add to this as well. And using another trick, we can share data across instances as well. And this helps save both on startup time and memory footprint. I talked about the fact that we are now honoring the resource constraints that you set up with Docker, both on the CPU side and on the memory side. And that we have a few different new options that you can use to specify the amount of memory to use. And finally, that we have also enabled and made our serviceability tools aware of container environments as well. And just as a final slide, as I said, there's more to come here. We're very committed to making sure that Java remains the first choice for deployments in cloud environments.